Let's talk about the oxidation of alkenes and alkynes via ozonolysis. To start, let's give you a little bit of context here. So, ozone is a very important oxygen containing molecule in this planet. We definitely need ozone in the upper atmosphere to prevent some of the more damaging UV rays from reaching the surface of the earth. But the molecule itself is actually quite toxic. In the lower atmosphere, it would cause major problems. But that's not to say that it wouldn't be helpful necessarily. So if you want it in some smaller quantities, you're trying to use it for a reaction, you can actually make use of ozone generators like the ones that you see right here. And technically they use some type of electrical current, a little bit of a voltage difference to excite dioxygen into radical species that eventually will form your ozone molecule. Now looking at the oxidation parameters for oxygen, you can see that ozone is one of the more oxidized versions of oxygen, and as such it is pretty reactive. In fact, the reduction of ozone down to dioxygen is got a positive 2.08 volt reduction potential, which makes this a very likely process. And at the same time, if you look at your organics like methane, um, ozone and methane are nowhere near overlapping in regions. So you could oxidize methane all the way to CO2. You could reduce ozone down to O2, at which point the layers overlap each other. And so this is telling you that you can enact some changes. Now, the changes that we're going to perform once more have to do with the alkene and alkyne components. So starting with the alkene right here, you can see that if we add ozone in the presence of zinc, we get to split up this molecule into two fragments. We have two carbonyls created. In essence, if you take the double bond right here and break it into two parts and add an oxygen at the end of each, you will get these two products that we see right here. One of them is a ketone, the other one is an aldehyde. That's completely dependent upon what groups are bound to the carbon. So let's go through the mechanism. Now this mechanism, unlike the one that I showed you for potassium permanganate, this is the known mechanism that has been proven. So this one you do need to know. So the first thing that happens is that your ozone molecule reacts with your alkene, and you do best to actually draw the Lewis structure of ozone, have the alkene attack ozone, and then have the opposite oxygen on the triatomic molecule cyclizing the entire process, the entire alkene to give you this intermediate. Now, when you end up forming this, the thing to notice is that technically speaking, you have now generated a molecule that contains two peroxy bonds, these oxygen-oxygen single bonds, which are not the most stable type of bonds around. So what ends up happening is that a rearrangement takes place that at the very least allows you to break and get rid of one of these oxygen-oxygen bonds and create a stronger bond in the process. So technically what happens is that this oxygen here on the right side provides electrons to the carbon next door, and then the carbon-carbon bond is broken to form a carbonyl. At the same time, the oxygen-oxygen bond up here has to have its electrons removed onto the middle oxygen, thus breaking that connection. And so you generate two fragments in this particular step, which is not necessarily a super great situation. On the one hand, yes, you do have your carbonyl oxygen, but you're also forming this oxonium and oxide counterpart that it doesn't look all that stable. In fact, it isn't. So what ends up happening is that this molecule right here, you can see right here one more time, the oxygen and the carbon trade places. Basically this molecule does a 180 rotation on its own axis, and what happens here is that it just positions itself so that you reform the cyclized product, but this time you're going to have oxygen carbon connections taking place as opposed to multiple oxygen oxygen connections. Alright, so here the oxygen brings its electrons to the carbon, then the double bond right here attacks the carbon over there, and then this double bond gives its electrons back to the oxygen bearing the positive charge. And so what you end up generating is now a structure that contains multiple carbon-oxygen single bonds and only one oxygen-oxygen single bond, which is your peroxy bond. This is the weaker bond in the entire molecule. So here's where zinc comes in to aid in the process of finalizing the reaction. Because what zinc will do is it has two electrons, two valence electrons that it can give away to turn into zinc 2 plus. And if it does do that, the two electrons can be given to one of these two oxygens, making the peroxy bond, which then implies that the electrons of that oxygen-oxygen bond will be broken and given to the opposite oxygen, forming this particular metallocyclo trioxacyclohexane structure. So what you can see right here is that the zinc is really just serving the purpose of breaking that oxygen-oxygen single bond. And here you just have a rearrangement take place. You have the electrons over here between the oxygen and the zinc moving over to generate a new carbonyl bond. At the same time, the carbon-oxygen bond here is broken, and those electrons are delivered to the carbon on the opposite end of this metallocyclohexane fragment. And lastly, the carbon-oxygen bond right here is also broken, and the oxygen is entirely given to the zinc and precipitates out a zinc oxide, while in the process forming the alkene and the aldehyde components that we talked about at the beginning of the slide. So this is the deal to keep in mind when we're dealing with alkenes. If you're doing oxidations via ozonolysis, if the alkene doesn't have a carbon-hydrogen bond, then you'll end up forming ketones. If you do have one hydrogen-carbon bond, then you will form an aldehyde. If you do have two carbon-hydrogen bonds, then you just form formaldehyde automatically. And for the alkynes, a somewhat similar picture happens, although here you will not make use of zinc at all, because what's going to happen is that ozone will react with the triple bond. Only two electrons out of the triple bond will be provided to make this new carbon-oxygen connection, giving you the intermediate shown here. A rearrangement will happen for the electrons in order to break one of the oxygen-oxygen bonds. So you'll have this double bond moving over here to form a carbonyl bond. At the same time, the oxygen-oxygen bond here on the lower left will be broken. And at the same time, the oxygen here on the right portion of the molecule will donate electrons to keep the carbon from losing electron density. In other words, to keep the octet rule in place for that carbon. So what happens right here is that you have broken that connection. So you've broken one of those weak oxygen-oxygen bonds, but this molecule is still not a stable molecule. And unlike the alkenes, the entire fragment is actually one molecule, right? So you haven't actually broken the connections completely. You've only broken one of them, but you still have one molecule. So what happens now is that the carbon single bond right here rotates on its own axis until the carbonyl here on the right side ends up on top. And here you have another rearrangement that takes place. The oxygen here donates electrons to this carbonyl. The carbon-oxygen double bond donates electrons to the carbon next door, and then the electrons right here donate their pi bond onto the oxygen next door. So you produce a pretty hot species, right? We have a cyclobutane with a cyclopropane. This doesn't look very stable, and in fact it is not, to the point where this will actually rearrange. And so what can happen right here is that the oxygen-oxygen bond can break, move over here to form a carbonyl bond, and that will kick out the electrons of the carbon-carbon single bond that will go over to this point to form another carbonyl. And so what you will end up producing is this molecule that contains three oxygens still, but notice that you no longer have ring structures, you no longer have carbon, actually oxygen-oxygen bonds present. This is known as an anhydride, which if you do treat with acid and water, it will basically break it apart into two carboxylic acid molecules. And so here the need for zinc is really not necessary, because you will generate already a species that is reactive enough to give you the acidic substance, the carboxylic acid in this case. So if your alkyne is internal, meaning that it doesn't have any carbon hydrogen bonds, you're just going to form carboxylic acids. But if you do have one hydrogen bound to the alkene, excuse me, the alkane, man, the alkyne, long day, sorry guys. What that will tell you is that you're forming formic acid, right? So instead of having a carbon group right here, you'll have an H, but it will still be a carboxylic acid. All right, so that completes the story for ozonolysis. In the next video, we're going to talk about, an example or two to give you an idea of how to approach these oxidations with potassium permanganate and ozone. And then we'll talk about the hydroxyl to halide conversions. All right, so see you in the next video.